Right, so in this video I'm going to have a look at the Leaving Certificate Higher Level Maths Paper 1 for 2019. Now we're going to do question 2. So here we have a graph of the function f of x, which is 3 to the power of x. So it's an exponential function. X is an element of R. It cuts the y-axis at 1, 0, 1 here. And what we have to do is draw a graph of the function 4x plus 1. So this is a linear function. So I'm just going to do a few points. We'll do 3 points, I think, and plot those 3 points, join them up. Really you only need 2 points, but you usually do an extra one just to be sure you haven't made a mistake. So let's take x, our function is 4x plus 1, and that'll give us our y value here. So let's start at 0. Take x at 0. We might take, let's see, we might take 1 as well. We'll go for 1 here, and then we'll take 1 out at the end here, which is 2.5. Do these 3 x values. So I'm going to put 0 in here, add 1, so that'll give us a y value of 1. For 0, 0 plus 1 is just 1. So our first point here is just 0, 1. So 0, 1 will be here. Okay, second one then, we want to put in 1. So that's 4 times 1 plus 1. So 4 1's 4, 1 is 5. So that will give us 1 and 5 here. So 1 is here, 5 will be around here. So we put a point here as well. Okay, and finally this should be 2.5 here. So let me just change that. That's 2.5. So we're going to put in 2.5 here and add 1. 2.5 and add 1. Well, 4 2.5s, that's 8, 9, 10, plus 1 will give me 11. So what I've got here is 2.5, 11. So here's 2.5, 11 is here, so I'm going to get a point approximately here. Okay, so we need to just join these 3 points up. Now, I'm doing this freehand. Obviously in the exam you've got to use a ruler, do it accurately. So this is going to be a little bit shaky, so let's see what we can do. Okay, that's as good as I can get it freehand, I think. A little bit wobbly around here, but you should be able to do a better job with that using a ruler. Okay, so that's part A1. Draw a graph of the function on the diagram. Okay, so next thing it says verify that f of x is less than g of x for x is equal to 1.9. We've got to use substitution. So you've got to put 1.9 into each function. So let's do that. We have f of x, and that's 3 to the power of x. We have g of x, and that's, I think, 4x plus 1. So we want to show that 3 to the power of x is less than 4x plus 1 for x equal to 1.9. So let's just stick 1.9 in here. So we've got 3 to the power of 1.9, and we've got 4 times 1.9 plus 1. So 3 to the power of 1.9 is 8.06, 8.0636, and there's a few more after that, but I won't include those. So we want to show that that's less than 4 1.9s plus 1 will just give us 8.6. So you can see here that f of x is less than g of x, for x equal to 1.9. Okay, and that's it for part 2. Let's look at part B then. We have proof by induction here, so we've got to show that f of n is greater than or equal to g of n, where n is greater than or equal to 2 and n is a natural number. So we have what we really have to prove here. So what we have to prove is that f of n is greater than or equal to g of n, or that 3 to the power of n is greater than 4n plus 1 for, this is for n greater than or equal to 2, and then as an element and as a natural number. Okay, so let's start then. First thing we've got to do here, and I'm going to write this out in detail here. So you've got to show that P2, the proposition, this is our proposition here, this thing here, so we've got to show that the proposition is true for n is equal to 2. So we've got to show that P2 is true, i.e. that the proposition is true for n equal to 2. So if we take the left hand side first, that's just going to be 3 to the power of 2, and the right hand side is going to be 4 times 2 plus 1. Well, 3 to the power of 2 is 9, 2 4 is 8, plus 1 is equal to 9. So is 3 to the power of n greater than or equal to 4n plus 1 when n is equal to 2? Well, it's actually equal to it, so it is true. So P2 is true, and that's the first step, to show that it's true for the first natural number that we're talking about in the question, which is 2. Okay, so now we're going to go on to part 2 then. Now we've got to make an assumption here first. So our assumption here is that the proposition is true for some value that we'll call k, so that the that our proposition is true for pk, for some value k. So we're going to assume that this is true, pk is true, that the proposition is true, pk is true for some value n is equal to k. Don't know what k is, but we're going to assume that it is true for n is equal to k. So in other words, we're going to assume that 3 to the power of k is greater than or equal to 4k plus 1. And what we want to prove then from this, we want to show that if this is true, if 3 to the power of k is greater than or equal to 4k plus 1, then the proposition will always be true for the next value after k, in other words k plus 1. So we want to prove that pk plus 1 is true. Given, in other words, given that pk is true. So in other words, if we assume this is true, then we're going to prove that the next number after k, pk plus 1, will be true. So what does that mean mathematically then? We want to, what we're actually going to try and prove is that 3 to the power of k plus 1 is greater than 4 times k plus 1 plus 1. So this is what we need to prove here, this bit here, given that this is true. Okay, so let's start. So if we just look at the left hand side again here first, the left hand side is just 3 to the power of k plus 1. Now we can break that down using the laws of indices. That's just 3 times 3 to the power of k. This is a 3 to the power of 1 here. 1 plus k is just k plus 1 if we add the powers here. So now what we know about this is that this is 3 times 3 to the power of k. And if we look back up here again, back up here, we see we have a 3 to the power of k being greater than 4k plus 1. Now down here we have a 3 times 3 to the power of k. So if we multiply this left hand side here by 3, we know this is true, so that means 3 times the left hand side here must be greater than or equal to 3 times the right hand side. So what we can say for definite down here is that this 3 times 3 to the power of k will be greater than or equal to 3 times 4k plus 1. 3 times 4k plus 1. And we know that that's just going to be equal to 12, 3/4, 12k plus 3. Now we know this is true because we've assumed that 3 to the power of k is greater than or equal to 4k plus 1. So we know this is true, so we know that 3 times the left hand side will be greater than 3 times the right hand side, and we've got the right hand side multiplied by 3 here. So we know that this is true. The trick here is to show that, remember, this is what we want to prove here. So is this thing here greater than the right hand side of what we want to prove? If it is, then 3 to the power of k plus 1 will be greater than 4 times k plus 1 plus 1. In other words, this is kind of a term in the middle here. We know that 3 to the power of k plus 1 is greater than this, but is this greater than this here? So in other words, we know that this is greater than this, but is this one here greater than all of this here? So this is our term in the middle. So that's what I'm going to prove, that this thing here, we're going to work on this being greater than this here. Okay, so let's work on that then. So is 12k plus 3 greater than or equal to the right hand side of what we want to prove? The right hand side of what we want to prove here is just going to be 4k plus 4 plus 1, which is 5. So that's what this simplifies to. Is that greater than 4k plus 5? Well, if we look at this, we can simplify this. We can take the 4k, bring it over here, we'll get 8k. We can take our 3, bring it over to this side, subtract 3 from both sides, we get 2. That will give us k being greater than 2 over 8. That will give me k greater than or equal to 1 over 4. So in other words, this here is true for any k greater than or equal to a quarter. But remember, all our k's will be greater than or equal to 2. All our n's will be greater than or equal to 2. So all our k's will be greater than or equal to 2. So this will be true always in our particular case, because we're only going to be using k's greater than or equal to 2. So, and that's really it. Just to write that out in English, we would say as n is greater than or equal to 2, then our k will be greater than or equal to 2. So k will always be greater than will always be greater than k will always be greater than Is it greater than or equal to 2 or greater than? Let me just double check that. Greater than or equal to 2. So it will always be greater than or equal to 2. Therefore, greater than or equal to a quarter here in this particular case. So, so in other words, pk plus 1 will be true if pk is true. And since we know that p2 is true, we check that in step 1 by induction. So we know that if it's true for 2, for example, if k was true, sorry, if k was 2, then we know that the proposition is true for k is equal to 2. We've just proven that it's going to be true for 3. In other words, k plus 1 in this case, which would be 3. If it's true for 3, it'll be true for 4, and so on, for all values of n greater than or equal to 2. So in other words, that's by induction. So by induction then, the proposition is true for all n element of n greater than or equal to 2. And that's really it. That's writing it out in fairly fine detail. Okay, so that's it for question 2.